Hi. Our task today is to shift some Boolean data. We are given an amount that we're going to shift in from the left. So if it's negative, it goes from the right. And then we're given the Boolean data as a vector or possibly a scalar. So we just have to handle that as well. And there are many different ways that you can do this. I'm not going to go through all of them, just one. If you want to get inspired by other ways that this can be done, go look at the transcript for the chat event that happened in preparation for this presentation. So let's start with some data. This is the sample that we're given in the problem description. And we're going to shift it by 3 different amounts. We're going to shift it 3 steps, and then 0 steps, and also -3 steps, so that's the other direction. And let's do all of this at once. So we're writing a lambda here, so we're going to define inline anonymous, and then we're going to apply it to each. We want it to map over these 3 shifting amounts, but each time we want it to not apply to separate elements of this Boolean data. We want to apply it on everything, so this encloses it. And then APL's scalar extension, it takes, when we have an each, it takes the one scalar on one side, for example, and 3 elements on the left, and then it pairs them up appropriately. So by taking this entire thing and making it into a scalar, then everything gets paired up correctly. And we can see that by having our function just create a 2-element vector or list of the left argument and the right argument. Left argument is denoted alpha, right argument is denoted omega. And we can see it pairs up the left argument elements with the entire thing on the right. Okay, so we're going to take this in 3 steps. The first thing is we're going to identify which data it is that we want to keep. So when we do the shifting with a positive number to the right, then as if it were, we're pushing in on the left 3 zeros, and the data moves to the right, and the last 3 elements then drop off the edge on the far right. So that means that the data we want to keep is all but the last 3 elements. We can use drop, but that gives us the drop from the wrong end, because 3 drops from the front and -3 drops from the rear. If we negate the number, then it goes the correct way. So we can see how these are the initial 5 elements, and over here we have the trailing 5 elements, and for 0 we didn't drop anything. We can save ourselves this parenthesis if only we had a function that's like drop, but takes the arguments in the opposite order, so the data goes on the left and the amount on the right. That doesn't exist, but we can define it inline anonymously by putting this confused frown called commute next to it, and that commutes the arguments of this adjacent function so that the arguments are given in the other order. I like writing it like this. So now we have the correct data that we want. Next step is identifying where we want to put this data in the final result. So if we get the length of the right argument and then enumerate the indices there, then we can see that when we shift to the right with a +3, we want these 5 elements to end up in these trailing 3 positions. When we're not shifting, then everything stays the same, and when we are shifting to the left, pushing in zeros from the right, we want the first positions. So in essence, we could say if we look at the indices, we can take this amount and drop that many elements from all the indices, and that gives us just the subset of indices where we want our data to end up. So that would be the left argument dropping the indices from the right argument. But we also need somewhere to, should we say, draw our picture. We have the data we want to put into the picture. We have the positions in the picture where we want to put it, but we need a canvas where to draw it, and that would be a array of the same shape that just has all zeros. And there are various ways we could do it, but a very simple way to do it is to do a zero multiply by, because these booleans are just numbers, or we could do a zero and, which also nulls it. So this works. And now we can take all the pieces and put them together. Oh, there's one more step before we do that. We are also given the case where the argument is a scalar. In that case, we want to normalize it to become a vector, which we can do just by raveling. So in magnetic comma, it ravels, it flattens the array into a just a simple list, a vector, which means if it's a vector already, it stays that way. If it's a scalar, then we make it into a one element vector. So now that's done. Then we take the data that we want to put in and we stick it in at the indices that we computed by dropping elements from all the indices of the length of the argument. And now we can see how we have shifted in 3 bits from the left and 3 bits that have fallen off on the right, and then we preserve these. For 0, nothing happened here, and for a negative number, we're shifting in from the right. And if we try this on a scalar case, let's say a 1, then it gets normalized to a vector, and in the case where we are shifting out too much, there's nothing left. We still just have a single 0. And in the case where we're not shifting anything, we preserve the 1 as it is. So this is our solution. But just one of many possible solutions. So go have a look at the transcript from the session, and maybe you even want to join in on a live event happening every Friday. Thank you for watching.